and I'll be talking about patch-level nuclear pleomorphism scoring using convolutional neural networks. I'll introduce my company very shortly. Virasoft is a medical imaging, let's say it's a medical software company which is focused on cancer diagnosis. So we have a product which we have developed and is powered by artificial intelligence to assist pathologists in their work with medical imaging. So I'll be presenting just a little bit of some of our results with you today. I'll start by talking about the aim of this work, what you would see in the introduction, and why this is important. And then I'll move on to the methods which we have employed on a very high level. I may not delve into so much detail since this is an industrial type presentation. And then I would show you the results and some possible discussions that may come out of it before I conclude in my last slide. Right. So in cancer diagnosis, slides are viewed, so samples are taken from the cancer patient and then they're digitalized using digital scanners basically. So the staining type is of hematoxylin and eosine. And these are the types of images that we typically view. The screenshot you see on your screen is actually from our web-based application. So we're able to view these H&E stained histopathology images. And based on what we see, we perform some automatic analysis. And the one I will be talking about today is called nuclear pleomorphism. Basically, in this analysis, the sample is analyzed and the severity of cancer is graded according to some standard grading. This grading is called the Nottingham grading system. So the pathologist, in a traditional way, the pathologist looks at this slide and he or she decides to give a grade. For example, nuclear pleomorphism grade maybe is 1, 2, or 3. In the next slide, I'll show you these grades. But what we do here is we try to automate this process so that pathologists can perform their jobs faster. Otherwise, there are lots of slides to grade and the pathologist can get tired. And because of that, there can be some issues with consistency or accuracy of the grading. So we are basically trying to mitigate these problems. And in this study, we're trying to find the most accurate classifier using deep learning. So what is nuclear pleomorphism? Nuclear pleomorphism basically tries to look at the variation in the nuclear size, the nuclear shape, the homogeneity, are the sizes the same, are they different? You know, based on all these factors, grades are assigned. So the severity is from normal to score 3, as you can see on the screen. So in the normal, it's obvious you don't see a lot of nuclei. In score 1, there are more nuclei. Yeah, I hope you can see the differences. We try to select the most distinct cases for you to see. The data we obtain is from our partner at the moment. Whoever we work with provides the data that we train networks with. The reason for this is the privacy concerns in the health sector. It will be really nice to share data across hospitals. However, it's not that straightforward. There's lots of regulations and procedures. So we say no problem. Give us your historical data. We would label it, and we would deploy our models on your site. So, in this study, the data obtained is from Acıbadem Hospital. We have a really good partnership with them, and from this data, we have been able to extract a total of 10,888 patches just for this study. And after augmentation, it increased to 43,552. The augmentation we perform is just basic rotation, flipping, since this is a classification task. One problem we face, however, is in score 1, you can see that there are very, very few samples. So if you compare score 1 to score 2, for instance, score 1 has 37, we had only 37 samples, and in score 2 we had over 4,500 samples. This is a classic problem of machine learning, but there are strategies to mitigate it. So thanks to open source and sharing in machine learning community, we have these state-of-the-art convolutional neural networks, the ResNet, the DenseNet, and the dual path networks. So these are classification models. They are readily available. However, most of them have been trained on ImageNet data, for benchmarking, and each of these networks have progressively performed better than the other. So ResNet, I would say, was the breakthrough after AlexNet. ResNet introduced the skip connections you can see in the diagram above. However, DenseNet takes it to another level. It provides skip connections, but across layers. So the last layer of the network, for instance, still gets raw information from the input image. So this is one of the reasons why DenseNet outperforms ResNet. The DPN is an interesting network because it is a hybrid network. So it takes advantage of both ResNet and DenseNet in its applications. Now, for all of these networks, we use the same data to train them. We use the same parameters. So the learning rate was the same. The loss functions were the same, and we use the same metrics to evaluate them. I would say a small note about the unbalanced data set that I talked about earlier, where we had very few classes in score 1. We tried several ways of mitigating this problem. We tried the oversampling of the minority class and the undersampling of the minority class. We also tried to use class weights in the loss function. However, the strategy that proved to be the best was using the class weights in the loss function. Again, I'm not going into so much detail about it. You may want to look it up, but in our experience and with this data, this is the strategy that worked the best. So what we were looking for was as low as possible loss. We didn't want to depend on accuracy because accuracy can be skewed. So we were looking for the network that gave the lowest validation loss. So our validation data was 10% of the total data. So training was 90% and validation 10%. On the loss curve on the right, I have marked the lowest validation losses for each network with bigger pointers. So ResNet with the square pointers and the red curve has the lowest validation loss at epoch 5. However, DenseNet and DPN achieve lower validation losses at epoch 8 and 7 respectively. But the lowest among the three was the DenseNet. Now we set the maximum number of epochs for 100, but there was early stopping so that if the validation loss didn't increase after a certain number of epochs, training would stop to avoid overfitting. So these networks performed quite well if you look at the accuracies, all over 90% accuracies. But this is a medical application, so we are very particular with optimization. Another issue with this is for implementation, we don't want a very heavy network. So I would say coincidentally, the DenseNet is not as heavy as the ResNet. It performs better, but the performance is comparable with the dual path network. We decided to go with the DenseNet because it's not as it has less parameters than the dual path network, meaning it's lighter, so it's easier to deploy this network actually. More results here, just to show the numbers for F1 score. F1 score it's important to look at the F1 score, especially in the unbalanced data set scenario. So again, we see the DenseNet performing better with a mean accuracy of 96% and an F1 score of 94%. Again, all the networks are not bad, but for our application, we need to really optimize it as much as we can. If we look at the scores individually, it seems the networks, it's easier for the networks to classify the score 2 and score 3 classes, especially with reference to the precision. However, for score 1, it's pretty bad, I would say. So even though I said earlier that our strategy was the best, it really is the best among the ones we have tried. But for score 1, it doesn't perform really great. But after consultation with our clinical partners, the pathologists, they said this is not an issue because score 1 is the rarest score. So in a score 1 accounts for less than 2% of the other scores. So even if the network may not be able to classify score 1 properly, it's not a big problem for them. But this is an ongoing work, and we continue to seek ways to improve these results. At the moment, that is where we are with this work. It continues to improve because we continue to add data to the network. We closely follow state-of-the-art work in deep learning for classification. And yes, that is it. So I have talked about the classification of H&E stained breast tissue. And then we validated 3 state-of-the-art CNNs, the DenseNet, ResNet, and the dual path networks. The DenseNet is the one we chose over the ResNet and the DPN because it performed better. It performed the best among the 3. And it reached a validation accuracy of over 95%. And on the test set, there's over 80%. I should mention here that these results are obtained from the test set, not a validation set. So this is totally unseen data. So even on the test set, it performs well over 95% in terms of accuracy. Thank you very much for listening to me, and if you have any questions, I'll be happy to answer.
Thank you for presentation, and I'm sorry for the confused. I was excited, and we have two questions, and please answer shortly because we have a time problem.
Sure.
The first question is, how do you see the future of machine learning or deep learning solutions in the histopathology area?
Okay. Let me answer that quickly. Machine learning has a very bright future in in histopathology area. In our company, I've just showed one of the applications. We have other applications of machine learning and deep learning specifically in histopathology. So it has a very bright future and it's moving very, very quickly. It is not going to replace pathologists. It will assist them and make the work faster.
Okay.
I hope that answers the question.
Okay, thank you. And the second question is, are the solutions you provide as Virasoft included in the clinical workflow? Are they actively used in the area?
Yes, we have several deep learning projects in Virasoft. This is one of them, like I said earlier. Another one, which is in a more advanced stage, is actually in use. All pathologists in Acibadem Hospital actually use this in our suite of software. It's also in our EduPath. So instructors use this remotely within the application for their lectures. So with students, this is used. We have deployed it, and it is for sale, if I may say.
What about your deep learning based solutions? Are they included?
Yes, this is what I just said. The deep learning based solutions are included. Nuclear Pleomorphism is one of them, which is what I've presented now. Another one is mitosis detection. That is in a more advanced stage and it is in use. But something I should say is they're constantly being updated, because as new data comes in, the model is retrained and updated continuously.
Okay, thank you very much for your presentation.
Thank you very much.